Okay, lattice enthalpy. Lattice enthalpy is a very important measure associated with ionic bond strength. Technically, the definition of lattice enthalpy is it's the enthalpy change required to convert 1 mole of an ionic compound into gaseous ions. But if you think about that, to take something that's bonded in the solid phase and to completely separate it into the gas phase, that means you have to overcome the attractions between those particles. So you have to break all the bonds. And so the stronger the ionic bonds, the higher the lattice enthalpy, or larger lattice enthalpy. Now you should be able to figure out, is lattice enthalpy endothermic or exothermic? And it's going to be important that you can remember that. Maybe pause and ask yourself, can you figure out, is it endo or exothermic, based on some general ideas that we have talked about throughout this school year. Okay, hopefully you paused and now you've unpaused. Well, lattice enthalpies are going to be endothermic because you're breaking bonds. You are separating particles. Okay, so up above right here, NaCl to Na plus and Cl minus, this would be a way to represent the lattice enthalpy of sodium chloride. Including state symbols is really important for this one because they're in the definition. This is the one for calcium chloride, so notice that on the left, the 2 is written here with the chlorine as the subscript because that balances the charges of the ions when they're together. However, on this side, there is no 2 written because chloride ions are not diatomic. So although chlorine is diatomic, the element, when it's a gas, but when you have chloride ions, so when it has this charge, it is not diatomic. So little details like that are important. Really, none of these ions, when we separate them out in lattice enthalpies, are going to be diatomic. So any subscripts that you start out with on the left should turn into coefficients on the right when you show a lattice enthalpy. Okay, so lattice enthalpies are very endothermic because we have to put in a lot of energy to overcome the electrostatic attraction between these ions. You should also be able to pick out and compare lattice enthalpies obviously on paper 2, but here you have them in front of you. You should be able to explain these differences. And on paper 1, you should be able to decide which compounds will have higher lattice enthalpies than others. The good news is it follows some very basic rules that you could summarize as Coulomb's law, which essentially is, as the charge on an ion increases, so if we increase ionic charge, we will increase the attraction between ions, and therefore we will increase the lattice enthalpy. And I can see that if I compare the first table here, which has alkali metal halides. So all of these ions are +1, and all of these ions here are halogen ions or halide ions, so they all have a -1 charge. Now, if I compare that to things in the tables below, in here, all of these metals have +2 charges, and then down here with oxygen, I have 2- charges, and then here I've got some +2 ions again, and here I've got oxygen with this 2- charge. And so you can see if you compare the values just roughly in the first table with the +1 and the -1 ions, and you compare it to the values in the tables below, where we have +2 ions, and then when we have +2 and -2 ions. Now I should probably be consistent when I write my charges. So if we want to write them all, let's write them all like this. Let's get out of oxidation state mode, and let's write them all with the number first, since now we're writing charges. Sorry about that. Okay, if I go back to my comparison, in this first table, there's only one of them that even reaches 1,000 kilojoules per mole. But if you look down at the bottom table, all of these ones with the +2 ions are all above 2,000. And when we go to +2 and -2 ions, we get over 3,000. So we can see that there's a real clear link that when we increase ionic charge from 1+ and 1- to 2+ or 2+ and 2-, the greater the charges, the greater the attraction, and therefore the greater the lattice enthalpy to overcome those attractions. So that's one really important rule. The second rule, which you can see in table 1 on its own, so these were the 1 plus ions, these are 1 minus ions. Within this table, I can see a trend that the lattice enthalpies are getting bigger in this direction. And if I think about those ions, and I'm trying to think about how they're changing, I know that as I go this way, I'm going up the periodic table from iodide to fluoride, and I know that this way I'm going up the periodic table. And that tells me that those ions are getting smaller. And so the other trend would be that as we decrease ionic radii, so how big these things are, then we're going to increase lattice enthalpy as well. And that's because smaller ions can pack more closely together, so the charges can get closer together. It also means that the charge of the ion is more dense, because if you have a 1 plus charge spread out over an ion this big, or you have a 1 plus charge spread out over an ion that big, the first one is more charge dense. And the more charge density you have, the greater the lattice enthalpy, the greater the attractions between the ions. So these things together kind of add up to just an overall rule about charge density. So as we increase charge density on an ion, we will overall increase the electrostatic attractions between the ions, and therefore we increase the lattice enthalpy. And so higher lattice enthalpies imply stronger ionic bonds and higher melting points for these compounds as well. So greater charge density, greater lattice enthalpy, greater melting point, stronger ionic bonds. Okay, so all summarized in one table. Lattice enthalpy gets brought up a lot on the HL exam. You should know its definition, know how to represent it in an equation. As shown here, state symbols are important. You should know it's endothermic, and you should know these various factors about charge and radii and charge density and how they affect lattice enthalpy, and be ready to explain them in words on paper 2.